December 23, 1944. Malmedy, Belgium. Snow fell on captured American positions as German Hauptmann Ernst Hoffmann sorted through crates of artillery shells. Each shell was stamped T-97 in small black letters. He noted unusual weight distribution, examined the fuse assembly, sketched the complex internal mechanisms in his field notebook. These American shells seemed unnecessarily complicated for simple-time fuses. He filed his report marked priority for Berlin ordnance analysis. The report reached Waffenamt headquarters 3 days later. Technical officers reviewed Hoffmann's sketches, noted the miniaturized components, and filed the report under advanced mechanical time fuses. Nobody investigated further. The assumption was absolute: radio proximity fuses were impossible. German researchers had attempted 37 different designs over 5 years. All failed. The vacuum tubes couldn't survive artillery launch forces. The batteries wouldn't maintain charge. The circuits couldn't function reliably. Therefore, what Hoffmann had discovered couldn't be what it appeared to be. In reality, Hauptmann Hoffmann had held in his hands the most revolutionary anti-aircraft weapon of World War II. The device that, 6 months earlier, had transformed the battle for London's survival. The technology that American factories were producing at 50,000 units daily. The weapon so secret it was protected at the same classification level as the atomic bomb. And German intelligence, blinded by their own failed attempts, looked directly at it and saw nothing. The story had begun 18 months earlier, 5,000 miles away, in a shabby laboratory at Pasadena, California's Caltech campus. Dr. Charles Lauritsen, a Danish-American physicist known for cosmic ray research, faced a problem the U.S. Navy insisted was unsolvable. Create a fuse that could detect aircraft proximity and detonate automatically. Make it survive 20,000 times the force of gravity during gun launch. Fit all components into a space smaller than a wine bottle. Manufacture it for under $20 per unit. Have 100,000 ready by December 1943. The Navy's skepticism was understandable. Vacuum tubes shattered under 100 g acceleration. Radio transmitters required pounds of components. Batteries degraded within months. Precision electronics cost hundreds of dollars per unit. Lauritsen's deadline demanded impossible miniaturization, impossible ruggedization, and impossible mass production simultaneously. Senior Navy officers allocated funding but privately predicted failure. They'd seen promising laboratory prototypes before. None survived real-world testing. Lauritsen approached the problem differently than German researchers. Where German scientists sought perfect individual solutions to each technical challenge, Lauritsen orchestrated parallel development across dozens of teams. He didn't need perfect vacuum tubes, just tubes good enough to function once. He didn't need batteries lasting years, just batteries surviving storage and activating reliably. He didn't need elegant circuits, just circuits that worked under impossible conditions. Good enough, mass-produced, deployed at scale, that was victory. By June 1943, initial Pacific combat tests proved the concept. The USS Helena engaged Japanese aircraft with VT-fused shells on January 5, 1943, achieving direct hits with impossibly low ammunition expenditure. By summer, the secret weapon was saving Allied ships throughout the Pacific campaign. But the technology remained classified above top secret. If a single fuse fell into Axis hands, Japanese or German engineers might copy it. The advantage would vanish. So proximity fuses were only authorized over water where duds sank out of enemy reach. Then came June 13, 1944. At 4:18 a.m., the first German V-1 flying bomb struck London, destroying a railway bridge at Grove Road, Bow. 6 civilians died instantly, crushed under collapsing masonry. By dawn, 200 Londoners were homeless. By week's end, V-1s were arriving at rates exceeding 100 daily. Hitler's vengeance weapon had finally arrived, a pilotless cruise missile carrying 1 ton of high explosive at 400 miles per hour. German High Command calculated that even modest success rates would deliver devastation exceeding the entire 1940-41 Blitz. London faced existential threat. British Corporal Thomas Keating manned a 3.7-inch anti-aircraft gun at Dymchurch on the Kent coast. Throughout the first week, his battery fired thousands of rounds at the distinctive buzz bombs crossing overhead. Hit rates were dismal. The V-1 flew too fast for manual tracking. By the time gunners calculated trajectories and set fuses, targets had passed. Shells exploded uselessly in empty sky while V-1s proceeded toward London. Keating watched impact flashes on the horizon each night, knowing his battery had failed to stop them. The mathematics of conventional anti-aircraft fire favored the attacker. German calculations predicted intercept rates below 5%. They were correct. But across the Atlantic, urgent meetings at the Pentagon were reaching different conclusions. The V-1 flew at constant speed and altitude, unlike maneuvering aircraft. It followed predictable trajectories. It presented a larger radar cross-section than fighters. Every characteristic made it the ideal target for proximity-fused ammunition. The risk remained: deploying VT fuses over land meant potential German capture of duds. But London's survival outweighed operational security. On June 27, 1944, authorization was granted. Proximity fuses would be deployed against the V-1 threat. The secret war was about to become visible to German observers who wouldn't understand what they were seeing. By early July, special ammunition convoys arrived at British coastal batteries. Corporal Keating and his crew received strict instructions. The new shells came in sealed containers marked with red bands. Every shell fired must be logged by serial number. Any dud sightings must be reported immediately for recovery teams. Crews were forbidden from discussing the ammunition's special characteristics. Keating noticed the shells felt different, slightly heavier toward the nose. He didn't know why. Nobody told him these shells contained miniature radio stations that would transform his gun's effectiveness. The first combat test came July 3, 1944, at 2:47 a.m. radar detected a V-1 crossing the coast at Dymchurch. Keating's battery received automated firing solutions from the new American SCR-584 radar system. They loaded the special red-banded shells and fired on command. The sequence felt identical to conventional firing. Then the V-1 exploded in mid-air, 300 yards from the nearest shell burst. Keating watched the flaming wreckage tumble into the channel and wondered what had happened. The explosion had occurred too far from the shell burst for fragments to reach the target. Yet the flying bomb had clearly been destroyed. At Flak Regiment 155W headquarters in the Château d'Attigny, Hauptmann Ernst Hoffmann compiled troubling V-1 effectiveness reports. During June, approximately 83% of launched V-1s had reached the English coast. Attrition was explainable: mechanical failures, fighter interceptions, barrage balloon entanglements. But July statistics showed concerning trends. Coastal anti-aircraft gun effectiveness was rising inexplicably. By mid-July, interception rates exceeded 40% in the coastal gun belt. By late July, they approached 60%. The mathematics violated known ballistic probability. Hoffmann's technical training told him this shouldn't be possible. German observers on the French coast reported strange phenomena. V-1s would be flying steadily when suddenly they'd be surrounded by flak bursts. But the explosions appeared to occur too far away for fragment hits. Yet the V-1s would tumble from the sky anyway, often with visible fuel fires suggesting fuselage penetration. Hoffmann considered several hypotheses. Perhaps British guns were firing new fragmentation shells with extended lethal radius. Perhaps observers were misjudging distances. Perhaps V-1s were more fragile than testing indicated. None of these explanations satisfied the data. Something fundamental had changed in British anti-aircraft capability, but Hoffmann couldn't determine what. The truth was operating invisibly at the quantum scale of radio physics. Inside each red-banded shell, a miniature transmitter generated continuous radio signals. As the shell approached the V-1, reflected signals intensified. When reflection strength crossed a threshold indicating proximity, circuits triggered detonation. The shell didn't need to hit the target or even explode nearby through conventional aiming. It exploded automatically when radio physics determined optimal fragmentation range. Every shell became a seeking weapon, transforming near misses into kills. The V-1's 400 mph speed became irrelevant. The gunner's aiming precision became less critical. The proximity fuse had changed the fundamental mathematics of anti-aircraft warfare. By August 1944, British defences had been completely reorganised around the new technology. General Frederick Pyle, commanding Anti-Aircraft Command, concentrated maximum firepower in a coastal gun belt between Dover and Beachy Head. Every gun was linked to SCR-584 radar providing automated tracking and fire control. Every shell was VT fused. The system operated with mechanical precision. Radar detected V-1s the moment they crossed the coast. Computers calculated intercept trajectories. Guns fired automatically. Proximity fuses detonated at optimal range. V-1s fell into the sea or over unpopulated areas. The vengeance weapon was being systematically neutralized by technology Hitler's scientists had declared impossible. Corporal Keating's battery achieved kill rates that seemed miraculous by June standards. Where his crew had once fired 2,000 rounds to achieve a single V-1 destruction, they now averaged kills with fewer than 100 rounds. The red-banded ammunition made the difference, though Keating still didn't know why. He simply knew that when they fired these special shells, buzz bombs fell from the sky with reliable consistency. His battery's tally board showed 187 confirmed V-1 kills by late August. Other batteries reported similar success. The coastal gun belt had become an impenetrable barrier that German intelligence couldn't explain. At Flak Regiment 155W, Hauptmann Hoffmann's August 28 morning report showed statistics that his superiors initially refused to believe. Of 94 V-1s launched toward England during the previous 24 hours, only 17 had reached London. Coastal anti-aircraft guns had destroyed 73, a 78% intercept rate. 4 more had been destroyed by fighters, and several experienced mechanical failures. The vengeance weapon's effectiveness had collapsed. Hoffmann's report included observer accounts describing V-1s being destroyed at ranges where conventional shells couldn't possibly achieve fragment density for kills. His conclusion was unavoidable: British defences incorporated some revolutionary technology that German intelligence had failed to detect. Emergency meetings at German High Command produced more questions than answers. Oberst Max Wachtel, overall V-1 offensive commander, ordered immediate tactical changes. V-1s would be launched at varied altitudes to complicate British targeting. Launch times would be randomized to prevent defensive preparation. Some V-1s would follow evasive dogleg courses. None of these modifications improved effectiveness. The British interception rate remained devastatingly high. Whatever technology they were employing, it wasn't dependent on predictable V-1 behavior. The weapons were being destroyed through some mechanism that German observers couldn't identify and German scientists couldn't explain. The German scientific community faced cognitive dissonance. They knew proximity fusing was theoretically possible. They'd attempted development themselves. But every German research program had concluded the engineering challenges were insurmountable for 1940s technology. Vacuum tubes couldn't survive artillery acceleration. Miniaturized radio transmitters didn't exist. Reliable automatic detonation circuits required components that couldn't be mass-produced. Therefore, whatever the British were doing couldn't be proximity fuses. There had to be another explanation. Perhaps advanced radar-directed fire control. Perhaps some new fragmentation shell design. Perhaps improved propellants extending lethal range. German analysts explored every hypothesis except the correct one, because the correct answer contradicted their own failed research. While German intelligence puzzled over impossible statistics, American production facilities were achieving unprecedented manufacturing scale. The Crosley Corporation in Richmond, Indiana, employed 12,000 workers producing 15,000 fuses daily. Sylvania Electric's Ipswich, Massachusetts plant manufactured miniature vacuum tubes at rates exceeding 400,000 weekly, with 95% of production dedicated to proximity fuse applications. Western Electric facilities supplied specialized components. Raytheon provided magnetrons. The entire American electronics industry had been retooled for a single purpose, producing tiny radio stations that could survive being shot from guns. By August 1944, production exceeded 50,000 units daily. Cost per unit had fallen from $732 in 1942 to $18 by late 1944. The learning curve of mass production had achieved what German craftsmanship couldn't match. Dr. Charles Lauritsen coordinated production across 110 compartmentalized facilities. No single factory knew the complete design. Workers assembled components without understanding the final product. Security was absolute. Every fuse was serial numbered. Every deployment was logged. Naval vessels patrolled the English Channel recovering duds before German investigators could examine them. The secrecy extended to Allied forces. British anti-aircraft crews like Corporal Keating didn't know why the red-banded shells worked better. They weren't told. The weapon's effectiveness depended on enemy ignorance, and maintaining that ignorance required keeping the secret even from the operators deploying it. The contrast with German production methods was absolute. V-1 flying bombs were manufactured in underground facilities using concentration camp slave labor. Tens of thousands of prisoners died in the Mittelbau-Dora complex, working under brutal conditions assembling Hitler's vengeance weapons. Each V-1 represented suffering and death in its creation. Meanwhile in Indiana, Massachusetts, and across America, workers voluntarily chose overtime shifts, motivated by premium wages and patriotic purpose. Most didn't know what they were building. Many were women whose husbands or sons served overseas. They assembled tiny components with precision, maintaining rejection rates below 2%, producing millions of devices that would save London without ever understanding their role in that salvation. By September 1944, the V-1 offensive had effectively failed. Of 8,564 V-1s launched from ground sites between June and September, only 2,419 reached London. Coastal guns destroyed approximately 4,200. Fighters intercepted 1,900. The remainder fell to mechanical failures and other causes. British civilian casualties numbered 6,184 dead and 17,981 injured, tragic numbers, but a fraction of German intentions. General Pyle calculated that without proximity fuses, casualties would have been 4 to 5 times higher. The technology had saved 20,000 to 25,000 lives. London had survived Hitler's vengeance weapon through invisible mathematics that German science insisted couldn't exist. German military leadership shifted resources to the V-2 rocket, which flew too fast for any interception. But V-2 production was limited, accuracy was poor, and strategic impact was negligible. The V-1 program had consumed enormous resources, approximately $500 million in development and production, plus the lives of tens of thousands of slave laborers, while achieving minimal military value. It had failed not due to British courage or German engineering inadequacy, but because American industrial capacity had produced a counterweapon at a scale Germany couldn't imagine. The vengeance weapon had been defeated by assembly lines, not armies. Throughout this entire period, Hauptmann Ernst Hoffmann continued filing intelligence reports attempting to explain British anti-aircraft effectiveness. His October 1944 analysis concluded that improved radar fire control combined with possibly enhanced fragmentation shells had created the observed effects. He never mentioned proximity fuses. The concept remained outside the boundaries of what his training told him was possible. Even when the Battle of the Bulge offensive in December captured American ammunition supplies including T-97 marked shells, German ordnance officers examined them, noted the complex mechanisms, and filed them as advance-time fuses. The assumption of impossibility was so complete that evidence literally in their hands remained invisible. May 1945. Germany surrendered. Allied intelligence teams began comprehensive interrogations of German technical personnel. When asked whether they determined how their V-1s were being destroyed, German officers expressed confusion. They'd theorized about radar improvements, suspected advanced fire control systems, but admitted they never understood the mechanism. When American interrogators showed them captured proximity fuses, explaining the radio trigger technology, German scientists' reactions were documented: disbelief, followed by shock, followed by humiliation. Dr. Herbert Wagner, who designed the V-1's control systems, examined a proximity fuse for 20 minutes before quietly stating they'd estimated such technology wouldn't be possible for another decade. The proximity fuse was declassified in September 1945. Navy Secretary James Forrestal's announcement called it the second most important military development of the war, after only the atomic bomb. For Corporal Thomas Keating, who'd manned coastal guns through the V-1 campaign, declassification brought understanding. The red-banded shells that had transformed his battery's effectiveness contained radio fuses he'd never imagined. For the women who'd worked at Sylvania and Crosley factories, assembling mysterious components through 12-hour shifts, it brought recognition. They'd saved London and hadn't known it. For Dr. Charles Lauritsen, it brought vindication. The impossible deadline the Navy had given him had been met. The impossible engineering had been achieved. The impossible mass production had been accomplished. For Hauptmann Ernst Hoffmann, who'd held proximity fuses in his hands at Malmedy and not recognized them, the revelation brought permanent lesson in the danger of assumption. German technical training had been excellent. German scientific capability had been world-class. But the assumption that, we cannot do it, therefore it cannot be done, had created intellectual blindness more effective than any Allied deception operation. The evidence had been available. The Oslo report in 1939 had mentioned proximity fuse research. Combat observations in 1944 had shown effects consistent with proximity detonation. Captured shells in December 1944 had contained the actual devices. But assumption had trumped observation at every stage. Germany had lost a technological race they never knew they were running, defeated by mass-produced electronics they'd convinced themselves were impossible. The proximity fuse's legacy extended far beyond World War II. Its technology evolved into modern air defense systems, radar altimeters, and electronic warfare capabilities. Its production methods demonstrated that democratic industrial systems could mobilize scientific and manufacturing capacity at scales totalitarian systems couldn't match. Its secrecy protocols established templates for protecting breakthrough technologies. But perhaps its most profound lesson was about the nature of modern warfare. Victory came not through individual weapon superiority or tactical brilliance, but through system-level integration of science, engineering, manufacturing, and logistics. The side that could produce effective technology at scale, deploy it with operational security, and adapt it to emerging threats would win. On August 28, 1944, when coastal anti-aircraft guns destroyed 78% of incoming V-1s in a single day, the nature of warfare had changed. The Germans watching their vengeance weapons fall from English skies never understood why. Their perfect engineering had been defeated by mass-produced solutions they declared impossible. Their tactical adaptations had been neutralized by technology that didn't require predicting enemy actions. Their intelligence services had failed completely to detect the weapon system destroying their offensive. And when they finally learned the truth, it revealed something more devastating than any military defeat: they'd been wrong about what was possible. The proximity fuse proved that in modern war, the capacity to innovate at scale mattered more than individual technical brilliance. America hadn't produced the most elegant solution or the most sophisticated design. They'd produced good enough technology in overwhelming quantities, deployed it with absolute secrecy, and adapted it rapidly to emerging threats. While German scientists crafted perfect weapons in limited numbers, American factories mass-produced effective weapons by the millions. While German intelligence assumed impossibility, American engineers achieved it. While German high command waited for wonder weapons to change the war, America was quietly deploying them. Dr. Charles Lauritsen reflected in a 1948 interview that the proximity fuse succeeded because it was designed for manufacturing from the beginning. German researchers had sought laboratory perfection. His team had sought production scalability. They'd accepted compromises in elegance to achieve reliability in mass production. They'd prioritized components that could be manufactured by existing industries rather than requiring specialized facilities. They'd designed for the assembly line, not the laboratory bench. That philosophy, more than any technical breakthrough, explained why American factories produced 22 million proximity fuses while Germany produced none. For Corporal Thomas Keating, who returned to civilian life in 1946, the war's most memorable moment came during his battery's final formation. Their commanding officer had finally been authorized to explain what the red-banded shells had contained. Keating remembered the silence as crews processed the revelation. They'd been firing tiny radio stations that listened for echoes. Shells that thought for themselves. Weapons that operated through invisible physics. For 2 years they'd used them without understanding. But they'd trusted the system, followed procedures, and saved London. Sometimes victory required faith in invisible mechanisms, in technologies beyond individual comprehension, in systems larger than any single participant could fully understand. The Germans never discovered what hit them until long after it ceased to matter. By the time Hauptmann Hoffmann learned about proximity fuses, the war had been over for months. The knowledge brought no tactical advantage, only historical understanding of a defeat so complete it had been invisible. They'd been fighting 20th-century warfare with 19th-century assumptions. They'd been defeated by mathematics and mass production, by assembly lines and automation, by a democratic system that could mobilize science and industry in ways totalitarian control couldn't match. The lesson was written in the statistics they'd never understood: 78% interception rate, achieved through technology they'd convinced themselves was impossible, produced by workers who didn't know what they were building, deployed by gunners who didn't know how it worked, destroying vengeance weapons built by slaves who died creating them. The contrast was absolute. Democracy's invisible strength had defeated tyranny's visible terror. And the Germans, watching their weapons fall from the sky, never knew why.